Next theorem on the congruence relation. If A is congruent to B modulo n and D divides to n, where D is greater than 0, then show that A is congruent to B module D. So what is given? A is congruent to B module n. So what is the meaning of A is congruent to B module n? That n divides to A minus B. What do we have? N divides to A minus B. And therefore A minus B expressed in the form n into some integer. So this is our assumption that A is congruent to B modulo n. This is given. So what is its meaning? That A is congruent to B modulo n means n divides to A minus B, means A minus B expressed in the form n into some integer. So this is given. And what we have to show? We have to show A is congruent to B module D. So when A is congruent to B module D, if D divides to A minus B, that is A minus B expressed in the form D into some integer. So here also we are given D divides to n. D divides to n. D is greater than 0 and D divides to n. Therefore, what we have, n is equal to D into some integer. So let it be K1. K1 is the integer notation for this integer. D divides to n by using definition of divisibility. What we have, n is equal to D into some integer. K1 is suppose the notation for integer, that integer. And so that we have to show A is congruent to B modulo D. When A is congruent to B modulo D, if A minus B expressed in the form D into some integer. So consider A minus B and then try to express it is in the form D into some integer. So but A minus B is n into K, and this n is what? dk1. Substitute n as dk1, and therefore what we have, A minus B is equal to D into, write this k1 into k2 as in one bracket, and this is integer because k1 is integer, k is integer, and the multiplication of two integer is integer, and therefore A minus B expressed in the form D into some integer. This implies D divides to A minus B, and therefore A is congruent to B module D. So this is the proof of the theorem number A. Then theorem number B. All these theorems are separated theorems. What is theorem number B? That AX is congruent to BX modulo n, and greatest common divisor of X and n is 1. Then prove that A is congruent to B modulo D. And is called cancellation law. That is the cancel X. But when we cancel X, if greatest common divisor of X and n is 1. So this is given. So what is given? Ax is congruent to bx modulo n. Implies what? N divides to ax minus bx by using definition of congruence relation. And therefore, a minus bx is expressed in the form n into some integer. That integer is suppose k. Then also we are given what? The greatest common divisor of x and n is 1. So n divides to ax minus bx implies n divides to take this x as common. Ax minus bx is equal to nk. So x as common, and therefore what do we have? N divides to a minus, because this a minus bx expressed in the form n into some integer. Therefore n divides to a minus bx, or take here x as common, and therefore n divides to a minus b into x. Therefore n divides to one of them by using the previous theorem. But the greatest common divisor of n and x is 1. The corollary on the Euclid's lemma. What is the corollary on the Euclid's lemma? The greatest common divisor of n and x is 1, and n divides to a minus b into x implies n divides to a minus n divides to suppose x into y. Then either n divides to x or n divides to y. But if the greatest common divisor of n and x is 1, therefore n divides to a minus b. So this is the corollary on the Euclid's lemma. That is, if a divides to b into c, and if the greatest common divisor of a and b is 1, then n divides to c. A divides to c. So see that corollary on the Euclid's lemma. So by using corollary on that Euclid's lemma, n divides to multiplication of these two means n divides to one of them. And so n divides to a minus b because the greatest common divisor of x and n is 1, or n and x is 1. This is given. So n divides to a minus b, and therefore, because n does not divide to x, because the greatest common divisor of n and x is 1, and therefore a is congruent to b modulo n. We have this, a is congruent to b modulo n, and it's called cancellation law. Then theorem number C, that the greatest common divisor of x and n is d, and ax is congruent to bx modulo n. This is given, and we have to show A is congruent to B module W, where n is what? dw. So the greatest common divisor of x and n is d. That is the round bracket x comma n means greatest common divisor of x and n is d. Means d divides to both. D is common divisor. So the first meaning of the first, that x, the greatest common divisor of x and n is d, means d divides to x as well as d divides to n, and d divides to x means x expressed in the form d into some integer, and d divides to n means n expressed in the form of d into some integer, but this integer is, here is we take k1, but here is the notation w is given in the theorem, that n is equal to dw. So use that W notation. So n divides to, here is we have n, d divides to x as well as d divides to n, because d is the greatest common divisor of x and n. And by using definition of greatest common divisor, d divides to both. D divides to x implies x expressed in the form d into k1, some integer. And d divides to n implies n is equal to d into some integer, and that integer is given in the theorem W. So, and obviously the greatest common divisor of this k1 and w is 1. Otherwise, d is not greatest common divisor of x and n. Then we have to show, we are also given in the theorem that ax is congruent to bx module n, implies n divides to ax minus bx. And then n divides to a minus b, take this x as common, and then a minus b x expressed in the form n into some integer. So z is the integer notation for that integer. So y n divides to a minus b into x means a minus b into x expressed in the form n into some integer. So let z be the that integer. Then substitute x as this value dk1. Substitute this n value of n as dw. So we have this equation, and cancel this d. We have the a minus b k1 is equal to wz. Z is integer, and this means a minus b into k1 expressed in the form w into some integer, means w divides to a minus b into k1. But the greatest common divisor w and k1 is 1, and therefore w divides to a minus b by using the corollary on the Euclid's lemma. That w divides to this both, multiplication of these two, and then w divides to one of them, but w, greatest common divisor of w and k1 is 1, therefore w divides to a minus b, and therefore a is congruent to b module w, because the greatest common divisor of w and k1 is 1. And therefore we have a is congruent to b module w, because w divides to a minus b. Then next theorem, that if n is greater than 1, be fixed, and a, b, c, d are arbitrary integers, then through the following property, that a is congruent to b module n, then a plus c is congruent to b plus d, and ac is congruent to bc module n, and a is congruent to b module n, then a raised to k is congruent to b raised to k module n. So first the proof of the first theorem, this theorem number 5, it is denoted by number 5. So what is given? A is congruent to b module n, and therefore what we have? N divides to a minus b, and therefore n divides to a minus b. So we have a minus b is equal to n into some integer, right? Either this proof or the another proof is what? Add c, subtract c. And then what we have? N divides to a plus c minus, take this minus sign common, b plus d, and this implies a plus c is congruent to b plus c module n, because n divides to this. Okay, so just add c, subtract c, and then take this minus sign common. So n divides to a plus c minus b plus d, and therefore a plus c is congruent to b plus d module n. This is the one way of the proof. The another method is what? We have to show what is given, a plus a is congruent to b module n. So what is the meaning? That n divides to a minus b, and therefore a minus b expressed in the form n into k for some integer k. Then consider a plus c minus b plus d, in bracket a plus c minus b plus c, and then what do we have? It is a plus c minus b minus c, that's minus c get cancelled, and then for a minus b, and it is equal to n k1, and therefore n divides to a plus c minus b plus d. So the proof, another format of the proof. Here similarly consider ac minus bc and express it in the form n into some integer. So ac minus bc is what? A minus b into c, and then a minus b is what? Is n k1, and then what do we have? N k1c, and therefore n divides to a minus ac minus bc, and therefore AC is congruent to BC modulo n. So, or write this proof that n divides to A minus B, and then write the proof of the this AC is congruent to BC modulo n. That n divides to A minus B, therefore n divides to C into A minus B. That is n divides to AC minus, because if n divides to X, then n divides to CX. Its multiples, and then therefore AC is congruent to BC modulo n. So either write this proof or this proof, that assume that A is congruent to B modulo n, write it mean that n divides to A minus B is equal to nk, and then consider A plus C minus B plus C, and express it in the form n into some integer, and consider AC minus BC and express it in the form A into some. That is this is the method, this method. The proof of the theorem is given by this method, another method, or the method given here. Then we have to show A is congruent to B modulo n, then A raised to K is congruent to B raised to K for some modulo n for some positive integer K. So n divides to A minus B implies n divides to A minus B into this bracket, because if n divides to X, then n divides to any number, any integer into X. So that integer is what? Suppose this is A raised to K minus 1 plus A raised to K minus 2 into B plus A K raised to minus 2, A B raised to K minus 2 plus B raised to K minus 1. That is adjust this bracket. And the multiplication of these two brackets is A raised to K minus B raised to K. Multiplication of these two brackets. And therefore, n divides to A raised to K minus B raised to K. And therefore, A raised to K is congruent to B raised to K modulo n. So this is true. That is, if A is congruent to B modulo n, then A square is congruent to B square modulo n, A cube is congruent to B cube modulo n, and so on. So the next theorem is important as far as the exam concerned, that let A and B be any two integers and n is a natural number. That is obviously n value of n is 1, 2, 3, 4, 5. And then prove that A is congruent to B if and only if A and B leave the same remainder when divided by n. So this is the theorem of type if and only if, and we know that if P if and only if Q is logically equivalent to P implies Q and Q implies P. That is the proof of the theorems of the type if and only if is in the two parts. So in part 1, assume P, prove Q, and in the part 2, assume Q and prove P. So what is the P statement here? A is congruent to B modulo n is the P statement. And what is the Q statement? A and B leave the same remainder when divided by n. That is where to show P if and only if Q. So assume P. So in part 1, assume P. Suppose that A is congruent to B modulo n. And what we have to show? We have to show A and B leave the same remainder when divided by n. So A is congruent to B modulo n. What do we have? Now we have to show A and B leave the same remainder when divided by n. So what is the meaning of A is congruent to B modulo n? Implies n divides to A minus B. And n divides to A minus B means A minus B expressed in the form n into some integer. Suppose that K is that integer. Therefore, we have A is equal to B plus nk, since that's minus B. Then apply division algorithm to B and n. That is, divide B by n. We have some quotient Q, we have some remainder. Okay, this is the division algorithm. That is, there exists Q and R such that B is equal to nq plus R, because if we apply the division algorithm to B and n, that is, divide B by n, we have some quotient, we have some remainder that are Q and R. Therefore, B is equal to nq plus R. Now, obviously, this remainder is what? Strictly less than the divisor and greater than or equal to 0. This is the division algorithm. That is, R is the remainder when B is divided by n. This is the meaning of this. B is equal to nq plus R means R is the remainder when B is divided by n. Now substitute this value of B in this equation number 1. So what we have? A is equal to value of B is nq plus R in plus nk. Then take this n as common. We have in bracket Q plus K plus R, where R is strictly less than n, greater than or equal to 0. Therefore, A is equal to this. And what is the meaning of this equation? A is equal to nq plus K plus R. That if we divide A by n, then Q plus K is the quotient and R is the remainder. So just what we have from this equation, that R is the remainder when A is divided by n. So here is this equation implies R is the remainder when B is divided by N, and this equation implies R is the remainder when A is divided by N, and means A and B leave the same remainder when divided by N. So this is the proof of the part 1, that assume P and prove Q, that A and B. What is our assumption in the part A? Part 1, that A is congruent to B modulo N, and what we have to show? A and B leave the same remainder divided by N. So we have R is the remainder when B is divided by N, and here we have the R is the remainder when A is divided by N. That means A and B leave the same remainder when divided by N. This is the part 1. Then in part 2, assume that A and B leave the same remainder when divided by N. And what do I have to show now? We have to show A is congruent to B modulo N in part 2. So assumption is what? Suppose A and B leave the same remainder when divided by N. And what do I have to show? A is congruent to B modulo N. So what do we have? That the meaning of this statement is what? A and B leave the same remainder when divided by N. That is A is equal to NQ plus R and B is equal to NQ dash plus R. Means what? What is the indication of these two statements? That A is equal to NQ plus R means Q is the question if A is divided by N and R is the remainder. And what is B is equal to NQ dash plus R means what? If you divide B by N, then Q dash is the question and R is the remainder. Why in both R is remainder is R? Because A and B leave the same remainder when divided by N. So by using this statement, what we have? If we divide A by N, we have the remainder R. If we divide B by N, then we have also remainder R. But we know that what are the questions? Q and Q dash. These are the two notations. Either use Q and Q dash or Q1 and Q2. But the remainder are same, and so use the R and R. So R is obviously strictly less than divisor N and greater than or equal to 0. And then A minus B. We have to show A is congruent to B modulo N. In part 2, what do we have to show? A is congruent to B modulo N. So when A is congruent to B modulo N, if N divides to A minus B. So consider A minus B. When N divides to A minus B, if A minus B expressed in the form N into some integer. So consider A minus B is equal to substitute A as NQ plus R minus NQ dash plus R, and then R and minus R become 0. So what do we have? N in bracket Q minus Q dash, and this Q minus Q dash is integer. Therefore A minus B expressed in the form N into some integer, and therefore N divides to A minus B, and therefore A is congruent to B modulo N. So this is the part 2nd, and proof of the part 2nd, that is the proof of the theorem of the type if and only if is in the 2 part. The first part is assume P, prove Q, and in second part assume Q and prove P. So in the next lecture we will see the definition of residue class module and some examples on that.